Hello students, my name is Shayan Mitra, faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management. Today I am going to take the lecture of electromagnetic wave. Subject code name is EC501. So let's start with the lecture. Today I am going to discuss the part of vector calculus. In the previous lecture, I have already described the basics of vector algebra, different kind of vector operations, different coordinate system and their transformation. This lecture now on, we are going to describe. We are going to give a lecture about. We are going to get understand the vector calculus. How the what are the different kind of sorry things we are going to describe the vector calculus. So let's start with the lecture. First, we are going to take a quick review of the previous lectures that we have already described the Cartesian coordinate system or vector polar coordinate system, where this is the differential displacement which is given by dx s of x, dy s of x y plus dz s of x z, and the ds normal area is this dy and dz, and the vector will be in the direction of s of x, and dx dz and s of in the vector will be in the direction of s of x y, and dz dy the vector will be in the direction of s of x z. The differential volume will be dx dy and dz, and differential displacement and differential normal area are vectors, whereas differential volume is a scalar product. And this is the pictorial depiction that I have already described. Let's go to the next slide. Differential elements in cylindrical coordinate system. In case of cylindrical coordinate system, the differential displacement is given as d suffix dl, and the value of dl will be d rho a suffix rho, dz a suffix z, and rho d phi a suffix phi, because we have already described that what is rho d phi is. Rho d phi is basically the value of rho d phi is the value of the value along the a suffix rho, and this is the value in case of from the angle law. We have already know that how to if we know the radial distance of a specific area and the angle which is the angle that has been that specific circular surface area is making with the center. If we multiply both the parameters, we will get the area of that specific region, and that's why we have considered rho d phi. Now the differential normal area is given as rho d phi dz a suffix rho, from this, where the area of this, the differential normal area is rho d phi dz, and the vector, the direction of the vector will be along the a suffix rho direction. And the same way we can describe the value of d rho dz, which is along the a suffix phi direction, and rho d phi dz, which rho d phi d rho, which is along the a suffix z axis, z direction. And differential volume will be same, rho d phi and dz. If you multiply them, we will get the differential volume of the specific infinitesimal small element of in cylindrical coordinate system. Let's go to the next slide. Differential elements in spherical coordinate system. Differential displacement is given as dr a suffix r d theta a suffix theta, the same process, and r sin theta d phi a suffix phi. This is the differential displacement. The differential volume is given as dv, because the r d theta into dr into r sin theta d phi. So we'll get the differential volume is r square sine theta dr d theta d phi. The differential normal area is given as r square sine theta is r square sine theta d phi, r square sine theta d theta d phi a suffix r sine theta dr d phi a suffix phi along the a suffix along the phi axis. This is along the r axis and this is along the phi axis. This is along the theta. This is along the phi axis and this is along the theta axis. That's why it's r d theta dr, r dr r d suffix r dr d theta a suffix theta. This is along the theta axis. So these are the different differential elements in Cartesian coordinate system, spherical coordinate system and cylindrical coordinate system. Now I will continue with the vector calculus. So let's start. The first thing we are going to describe is the line integrals. Now what is line integral means? Line integral is defined as any integral that is to be evaluated along a line. A line indicates a path along a curve in space. As an example, if function or vector f represent the force acting on a moving particle along a curve AB. Suppose this is the curve. Now the example of function f represents as an example, this is the function f that represents the force acting on a moving particle along a curve AB. Along the curve AB, the function f is represented as force act is this particle is moving along the AB axis, AB path, and a force f is acting on that moving particle. Then the line integral of function f over the path described by the particle represents the work done by the force in moving the particle from A to B. The line integral around the closed curve is called the closed line integral. So this is the line integral. Now this is the sign of the line integral. This is the closed, because it is a closed path, so it has been described with this, and this is the vector A and this is the displacement vector. Now first we have to realize what is the purpose of a line integral. Now the purpose that has been served by a line integral has been written here. That is, the line integral of function f over the path. Now line integral of function f. Now what is this function f is doing? This function f represents the force that is acting upon a moving particle along the curve AB. Now if we take a line integral, suppose there is an open path. The path is that this particle is moving along this path from A to B, and during that time when the particle is moving, there is a force that is acting upon that particle. Now if we take a line integral, now this is a closed path, so we have yes, this is a closed path, that's why we've taken this sign. It is a closed integral. Suppose this path is broken, it is not complete, so what we will take, that this particle is moving along this direction from A to B, and that force F is acting upon that. So now if we take a line integral of function f, we will get that the line integral of the path described by the particle represents the work done by the force in moving the particle from A to B. It is a physical representation. Now if we take a line integral of function f, the line integral will provide us the information of the work done by the force in moving the particle from A to B. Now if we take a line integral of function f, it will give us the work done of the in moving that particle using that force, moving the particle from A to B. Now from A to B, if we take a integral where the lower limit is A and the upper limit is B. Now if we take a line integral of function f, it will provide us the work done by the force in moving the particle from A to B. Now if we take a line integral of function f, it will provide us the work done. Now the force will be acting upon upon some particle or element. So this is the uh, physical representation of line integral. The line integral around a closed curve is called a closed line integral, that I have already described. So let's go to the next slide. Now the surface integral. Now the first thing what you have to understand is the line integral. The only thing that you need to understand is the physical, the feature of line integral. Now if we take a line integral of a vector, we will get to know the feature or the characteristics of that vector, which if we take a line integral of a specific vector, we will get the characteristics or the phenomena that has been created by the specific vector. Now suppose if we take a line integral of a vector f, we will get the work done by the vector f on the moving particle from line A to B. But if we take a line integral where the lower limit and upper limit are A and B respectively. So let's go to the next slide. This is the now we are going to describe the surface integral. Now what is the surface integral and what is the specific why the surface integral is used? That is going to we're going to describe that. Now consider a vector field A. This is the vector field A, continuous in a region of space containing a smooth surface S. Now that's why now if we take a line integral, here the vector is displacement length and this vector. Now this is the dot dl. Now it is the infinitesimal small displacement value. So this it will give us now it will give us the nature of the vector along this path. Now if you take a if you to understand the surface integral, what we will do? We will consider a vector field continuous in a region of space containing a smooth surface S. A smooth surface or any surface basically. Now let's understand how the surface integral works. Now the surface integral of vector A, which is continuous in the region of space containing a smooth surface S. Now suppose electric field is a vector field. Electric field will be working on a space containing smooth surface. Now this surface integral of A through S can be defined as epsilon, where now if we take a surface integral, what we will get the surface integral, and this is the surface, the direction of the vector is normal to that surface. Now for a closed surface defining a volume, the surface integral becomes closed surface integral and is denoted as this. Now if we have open path, we take a line integral of the specific vector. Now suppose the same vector is there but we have a closed path. Now if we take a line integral of the closed path, we will get a surface integral. Now if we take a surface integral of a closed path, that is nothing but will become a volume integral. That is what I have described. That for a closed surface defining a volume, that surface integral becomes the closed surface integral and is denoted by this, and it represents the net outward flow of flux from surfaces. Now that is important. That in case of line integral, what we have in case of line integral, the vector component, the resultant of line integral will give us the work done of a force in the specific direction. Now if we take a surface integral of a specific vector, suppose this vector is vector A, it will represent the net outward flow of flux from surfaces. This is the realization that suppose in this space this vector is continuous. Now if we take a surface integral, it will provide us the net outward flux of vector A through this surface. This value has been determined using surface integral. Now this is volume integral. Now what is volume integral means? Let V be a volume bounded by the surface S in this xyz. Be a function of a position defined over V. If the volume V is subdivided into n elements of volumes dV1, dV2, dV3 and dVn, in each part let us choose an arbitrary point, this. Then the limit of sum is this, as n is equal to infinity and dvi is equal to 0, is called the volume integral of this point over V and is denoted by this. And this is the point. Now this is the mathematical representation of volume integral. Now if we take a line integral of a closed path, we will get a surface integral. Now if we take a closed integral of a surface integral, we will get a volume integral. From line integral, we will convert it to surface integral. From surface integral, we will convert it to volume integrals. Now these are the mathematical representation, that is the significance of line integrals, surface integrals and volume integrals. Now let's go to the next slide. Now before getting into the Taylor operator, that we have to understand this, all this integrals format will be useful in deducting to get a realization of electromagnetism, and from that we will jump to the Maxwell equation using these three specific significance, where the line integral has been used in a specific way, the surface integral will provide you the net outward flux of the specific vector, and volume integral will provide you the whole realization of the volume integral. So let's go to the next slide. Now the important factor is this is known as a Taylor operator. Now what is a Taylor operator? It's basically a differentiation vector which has been used to differentiate this operator has been used to differentiate in the vector along x-axis, vector along y-axis and vector along z-axis. To get the differential value of a vector along the x-axis, along the y-axis, along the z-axis, we use the Taylor operator, where the I is basically the unit vector. I, j, k are the unit vectors along the x, y, z axis respectively. Now the gradient of a scalar function is a vector quantity. Now this is del f. Now this has been operated. The gradient of a scalar function is a vector quantity. Divergence of a vector is a scalar quantity. The curl of a vector is a vector quantity, and the Laplacian of a scalar is this. Now for the upcoming slides and the lectures, we are going to describe the gradient of a scalar, divergence of a vector, and the curl of a vector, and the Laplacian of a scalar, and the physical interpretation of all this mathematical operation and their significance. So let's go to the next slide. Now first, here we have a del operator. The del operator is a vector differential operator and is denoted as del phi, that we have already described. And in Cartesian coordinate system, the del operator is working as this, and del operator cylindrical coordinate system will act as a this, and in del operator in spherical coordinate system will act in this way. Now as we have already described in previous lectures, that how we can transform from x, y, z Cartesian coordinate to cylindrical coordinate, from cylindrical coordinate to spherical coordinate, and that's why we use different del operator in different coordinate system. In case of Cartesian coordinate system, we have this del operator. In case of circular cylindrical coordinate system, we have this del operator, and in case of spherical coordinate system, we have this del operator. Let's go to the next slide. Now this is the gradient of a scalar. Now how it works, we are going to describe how gradient of a scalar works. Now suppose t. Now another thing that we need to understand, we have to remember the gradient of a scalar is a function, it is a vector quantity. Now if we take a gradient of a scalar function, we will get a vector quantity. Now how we will get that? We will operate on a scalar function. We will operate on a scalar function using the del operator. if we apply a del operator on a scalar function that is known as a gradient of a scalar function, and it will be signify as a vector quantity. It means we just we take a the gradient means we just take a we will operate on this scalar function using the del operator. But in case of divergence of a vector, we will take a dot product of del operator and the specific vector, and it will provide us with a scalar quantity. In case of curl of a vector, the same thing. This is the del operator, and it will apply on this vector in a cross product format, and you will get a vector quantity. So this is the del operator in different coordinate system, and this is the gradient of a scalar. Now how the gradient of a scalar works? Now, as we have already discussed, that gradient of a scalar will provide us a vector quantity. Now how it will work? Now suppose T1 is the temperature at P(x,y,z). Now this is the point P(x,y,z), and this is the temperature. Now, and suppose the temperature is infinitesimally increased in x-axis, y-axis and z-axis in T2, and the temperature at P2 as shown. The PT is, this is the P2. Now for P1 we have increased, we have this position has been changed. We have increased the value of x around the x-axis, around the y-axis and the z-axis with the value P2. Now in P2 the temperature will be different. Now the differential distance in dx, dy and dz are the components of the differential distance vector dl. The dl is dx, we have already know what is dl is. However, from the differential calculus, the differential temperature will be this, and this is the differential temperature. Why? Because the differential temperature from this and this is dx, dy and dz. So now it has been operated on, and we will get the differential temperature, and this is the gradient of a scalar. Now for circular cylindrical, the same process, we will get this. And for spherical coordinate system, this is the equation. For we have to remember the difference between the cylindrical, spherical coordinate and Cartesian coordinate. Now we have to find the gradient of these scalars. These are the scalar vectors. Now if we put the del operator on these functions, on the scalar function, we will get a vector quantity. How? This is the e to the minus z sin 2x cos h y. Now if we put del operator on this value, we will get this. We will operate on this del u del rho. We have operated on rho square z cos 2 pi. Now rho and phi provide us that it is in circular cylindrical coordinate system. So we will use this specific del operator. For this function we will use this operator, 0 1 1 0 del u del z a suffix z. So if we operate on this function using del rho, other variables will be constant, and the first operator on rho. So the coordinate, the differential value is this, and in this it will operate on del phi. The function is cos 2 phi, so we will get 2 rho z sin 2 phi, and minus sign will come up here, and because there is a 1 by rho, so we will cut that and we will get 2 rho. Now if the del of del z will operate on u, we will get rho square cos 2 phi az, because in z the value of z will be 1 after differentiation, and we will get rho square cos 2 phi az. And the same thing will appear in using gradient for spherical coordinate. The same formula will be used, and we will get the different, for specifically spherical coordinate we have a different del operator signature, and we will use that. We will operate on the function and we will get these values, and all these are vector quantity. So these are the today we have learned all these vectors. We will end this lecture today here, and we will thank you all.